calculus. So everything we're going to do in here is we're going to look at logarithmic functions. And the first idea is we want to look at the definition of a logarithm and just kind of review that for a minute. So that's a super important thing to know, is the different forms. You have an exponential and you have a logarithmic form that you want to be able to interchange from. So a couple of examples on this, like if you had something like this, I'll just do something, make something up, like let's say that you have the log base 2 of x, or let me use a specific number. Let's say log base 2 of, say, 7 is equal to something like z or something like that. Okay, let's just say we have that. Well, when you change this to an exponential form, it goes like this. This just means the same thing as 2 to the z power is equal to 7. Okay, those are the ways that you interchange those. Another example, I'll write something down that you know. Like, for instance, if you had 10 to the second equals 100. That's an exponential form. If you change that to a logarithmic form, what you say is this. You say log base 10 of 100 is equal to 2. Okay, the key thing on this to pay attention to is these two things that I'm highlighting right there, those are the bases. Okay, the base, that's what you're raising, you're taking 10 to a power. That's the base of the logarithm, those things match up. Okay, and then the other thing you want to pay attention to, and get this in mind, is when you do a logarithm, the answer to a logarithm is an exponent. That's a worthwhile thing to write down. The answer to a log is an exponent. Okay, so it's another way of writing an exponential expression like that. So you want to be able to interchange those things back and forth. You guys remember some of that from your past? Okay, you want to get solid with that. Let me just kind of show you, see if you remember a couple things. There are times when you can do a logarithm in your head. Okay, for instance, let's say that you had log base 2 of 8. What's the answer? Remember, the answer is an exponent. 3, right. How do you know it's 3? Because 2 to the third is equal to 8, right? Okay, that's the idea. Here's another one. Let's say that you had log base 7 of 1. The answer is an exponent. What is it? 0. Good. Why? Because this base to the 0 power is equal to 1. So it's another way of writing an exponential expression. Okay? Now, if you encounter something like this, log base 7 of 5, you have to use technology to get that, because you don't know what power of 7 is 5. So that's the idea. Okay? So the next thing I want to look at a little bit is just kind of talk about the graphical relationship between an exponential and natural logarithm. That's real important. That's the exponential function, which we've looked at. And then the inverse of that is the natural logarithm, like that. I want to go through and show you where that comes from. So let's find the inverse. I want to just review this. And let's write down y equals e to the x. And let's go over how to do an inverse. That's actually something we reviewed at the very, very beginning of the semester. Okay, how to do inverses. So if I want you to find an inverse of a function, what do you typically do? You switch the variables. So let's switch the variables. So we have x equals e to the y, like that. Okay. Next thing you got to do is you got to solve for y. Well, the way that you solve for y is you have to know something about you got to know something about logarithms. Okay. So the idea is going to be this. Remember, I said when you have a logarithm, the answer is an exponent. The answer is y. The logarithm is the base. The base is e, so it's like that. Okay, so what I'm doing is I'm just rearranging that in a log form like that, and we know that log base e is ln of x. So that is the inverse. That's a simple way to show you that those two things are inverses of each other. Okay, so the big conclusion that you draw when you study logarithms in college algebra is you want to know that these things are inverses of each other. So the inverse of the logarithm is just we just say f inverse of x is equal to e to the x, like that. So those are the inverses of each other, okay? Another thing I want to show you on this is this, and see if you remember this. That point right there is 1, 0. That's on the graph of the natural logarithm. That point right there is 0, 1. Okay, what's the deal with those points? They're backwards. They got switched, okay? So what you would find on this is no matter where you are on these functions, those points would be switched, okay? Those are kind of the main points are right there. And then the other thing is it's symmetric about this line y equals x. So if you can imagine folding your paper across that line, they would match, wouldn't they? And the reason is because those points are backwards. That's how it causes that symmetry, okay? So that would be be the idea. All right, let's move to the next page, and we're going to review some properties here. Log properties are a really big deal in this section, and in the future, when you encounter logarithms, you want to know all these properties. So I'm going to quickly review all these things. Property number 1 is the most important because it's where all the rest of them come from. So let's do that one more time. I'll just pick something kind of at random here. Let's use a sensible expression, say like 4 to the third equals 64, okay? If you change that into a log, think of it this way. Remember, the answer to a logarithm is an exponent, so that's all by itself, okay? The base of the logarithm is which number? What's the base? 4. The base is what you're raising to the third power. Then you have that. So the key thing on that is make sure you know how to rearrange those things. That's incredibly important, okay? A lot of these things you don't have to memorize because you can figure them out, okay? What this one is saying is if you had a log of any base, that could be an 8, of 1, the answer is 0. Don't memorize that, understand it. Why is that true? Okay, the reason is because what? 8 to the 0 is 1. Okay, so anytime you take a log of 1, you're going to get 0 no matter what the base is. Okay, that comes from the exponential form. Okay, this is another one that it's nice to memorize, but you don't have to because you always can figure it out. This one goes like this. Let's say that you had something like log base 5 of 5 to the second power. Okay, the key thing is this base is matching that. Okay, according to this property, the answer to this problem is 2. That's it. And there's a couple of ways to show you this, and it's always going to be the same way. It goes like this. So if you wrote this thing in exponential form, let me show you what you would get here. Okay, so I would say 5 to the second. I take that base to that power. That's going to be equal to this value like this. That number to that is equal to that. It's always going to be true. Okay? If you don't like it that way, you'll like it this way. I bet you'll remember this way even better. Okay? When you're in college algebra, do you remember what you were told that you could do with that too? You can bring it down. You guys remember that? Okay? So that gives you like 2 times the logarithm base 5 of 5. What's the answer to that logarithm? That's 1, right? Why? Because 5 to the first is equal to 5. Okay? Like you're just figuring out what power of 5 is 5. So 2 times 1 is 2. Okay? So what that's saying is if you encounter this situation, then that exponent is the answer. And I know in my Calc 2 class, we do that all the time. It shows up all the time. We see it a lot. Okay? The next one you probably saw in college algebra, you probably did very little with it. This shows up a lot in Calc 2. Goes like this. If you had an expression like, let's say that you had 8, and in the exponent you had a log base 8 of 2. According to this, the answer is 2. Okay, the key thing is this number has to match that. If they match, then the answer is staring you right in the face. Okay? Now let me show you where that comes from. It's actually very easy to prove this. And I'll see if you follow this or not. So write this down. I want you to write down log base b of x is equal to log base b of x. Okay? You would agree that's true, right? Has to be. Okay, I wrote the same thing twice. Now see if you follow this or not. Sometimes students don't follow this very well. But we're going to change this to exponential form. When we change something to exponential form, we write down the base, right? And then what's the power? Whatever's over there. Okay, so we say b to that power, okay, is left over is this thing. Do you guys see that or not? Some students see that okay. A lot of times students don't see that very good. It's no different than what we did here. Up here we had 4 to the third is 64. Here we just do b to this thing is equal to x. That's where it comes from. That's how I figured that out. Okay. Then the next thing I want to look at is these properties you'll do quite a bit as well. So these kind of go like this. I'm just going to give you maybe one example of each. And I'm not going to do a proof of this. I'm going to do more of a calculator demonstration, I guess, is what I'll do. So let's say, for instance, that you had the log of 7 times 3. According to this, that's the same as the log of 7 plus the log of 3. Okay, I'll just show you. This is not a proof, it's a demonstration. So if I did the log of 3 times 7, which of course is just the log of 21, I get that. If I do the log of 7, and then if I add to that the log of 3, I get the same answer. And you always will. Okay, it always works. That's not a proof. It just shows you that it works. Okay, and then this one, I'll do the same thing. This time I'll do an ln just for something different. So if we had like the ln of 7 over 5, that's the same as the ln of 7 minus the ln of 5. So if you have a log of a fraction, then you can do the difference of the logs. So if I did this on a calculator to just demonstrate the log of 7/5, it's going to give me some decimals. Does that. And then if I did ln of 7 and then subtracted ln of 5, you'll see I get exactly the same answer. Okay? You guys remember that? Okay. And then the next one, usually students remember this one okay too. If you had something like the log, let's just say you had a log base 10, which is just a log on the calculator of something like 7 to the third. According to this property, you can bring down the 3, and then you can multiply it by the log like that. And they work out the same. You could do this as a quick demonstration on a calculator. You could go log of 7 to the third, like that. That would give you that answer. Well, if I did 3 times the log of 7, then that should give me the same answer. Okay, and it does. All right, you guys remember that? Okay, so that's the idea. You do that a lot when you're working with exponents and solving types of equations. Okay, this one right here just says this. You do this a lot in equations. If you had something like log base 5, say, of x squared plus 1 is equal to, say, log base 5 of 5, or whoops, I didn't write that right. Or I'll say something like maybe 10 or something like that. Well, what you can do is just take off the logs. Okay, what it's saying is since these expressions are equal, then these two things also have to be equal. That's what that's saying. So you can take off the logs. It's not that you cancel them, it's just you remove them, or you have the ability to take a logarithm of both sides of the equation. So those are the typical properties you look at in pre-calculus or college algebra. The other thing that you want to make sure you know in this section is change of base formula. That was on your first test. We did that very quickly at the beginning of the semester because I knew it was going to show up again. So as an example, real quick, if you were going to do if you needed to do, for instance, the log base 9 of 20, okay, you do it like this. You just do log 20 over log 9, or you can do ln 20 over ln 9, then you go to your calculator. Okay, you guys remember that? Okay, so that will show up, and one of the reasons change of base formula is important is because it'll keep you from having to remember another derivative formula, and when we get to that, we'll talk about that. Okay, now I'm going to get into the calculus here a little bit. So, since we're talking about derivatives, our goal on this is to figure out what the derivative of the natural log is, okay? So what I want to do on this first of all is we're going to just see if we can graph out a derivative, okay? So I'm going to try to graph the derivative on this one. I want you to do this kind of like this. I'm going to have you draw a graph to the side of it, and let's just kind of put this together like this. So just make yourself an XY axis, and we're going to start looking at the derivative. Okay, now this is the graph of the natural logarithm function. One thing that happens on this is you want to remember if you have a logarithm, that number has to be greater than 0. You can only do a log of a positive number, okay? So let's look at the slopes of the tangent line like this. Okay, let's start right here. Okay, let's say that you have a right there. What kind of a slope do you have there? First of all, positive or negative? Positive. Is it big or little? That's very steep, so that's very big, right? So that means that you would have very big positive numbers on your derivative there, right? Really big numbers, okay? Let's go to let's say like at 1. Okay, at 1, let's kind of estimate what that tangent line might look like. It's a little hard to tell, but that looks like kind of a 45-degree angle, okay? What did we say the slope of a 45-degree angle was? We said 1, okay? Remember, we're graphing the slope of the tangent line. So it looks like maybe when you're at 1, the value of the derivative is 1 like that. And what's happening on this is these derivatives are always positive. So if you went way out to 6, well, you still have a positive derivative, right? But what's happening to that derivative? Is it getting bigger or smaller?
Smaller.
It's getting smaller, exactly. So what happens to the slope of the tangent line? It gets smaller. So those values we're going to expect to get smaller. Now, do you think that that tangent line will ever get perfectly to 0? No, it actually doesn't, but it gets close. Because a logarithm does not have a horizontal tangent line, it just gets close to horizontal. So what you're going to have on this derivative is going to go like this. If you just kind of keep plotting these points out, it's going to do that. It's never going to reach 0, but it's just going to get close to it. So this would kind of be a logical way to think through what the graph of the derivative might be. What do you think? Is that logical? Okay, so that's what the derivative looks like. Now, that may be something that you know or maybe you don't know. What we're going to look at is this really is the graph of y equals 1 over x. That's what that is. Okay, if you put in 1 over x on your calculator, you actually get something like that, and then you kind of get a little region over there that looks like that. So we're not going to prove that the derivative is 1 over x. I'm going to demonstrate that it is just by doing a difference quotient, and I just took this out of the book because I don't want to do this on my calculator. So what I'm going to try to show you on this is let's kind of start by saying getting this difference quotient put together like this. So let's say that we have, and let's write this down. I want you to at least write this down. So f prime of x, if you put a logarithm in a difference quotient, it would go like this. You'd have the limit as h goes to 0 of ln of x plus h minus ln of x all over h. Remember, what we're trying to work with is we're trying to work with determining what the derivative of a natural logarithm could be. Okay, we kind of know what the graph of the derivative looks like now, so we do that. So what I'm going to show you is I'm going to show you a pattern. This is a nice way to help students see this. So basically what I'm doing is we're going to look at what happens, say, if x is 2. If I just plug that in like that. Now what I did on this, now if you did this on a calculator, and if you actually graphed that, which you could graph, and then you just made the h's close to 0. See, what I'm doing is I'm making h go to 0 because that's what we want to do in the definition. Look at these numbers. Where are they going? What would you predict that they would be going to? Now, it looks like they're heading towards a half, doesn't it? Okay, so it looks like it's about 1 over 2. Okay, like that. Okay, well, what I did on the next thing here is I said, well, let's change that to 3 now. Like that. In the difference quotient. Where does it look like it's heading? to a third. So, I mean, that doesn't prove anything, but it kind of begins to make you think something. What do you think would happen if you did 4? 1/4. How about 5? 1/5. If you took the time to do it, that's what you would be finding. So it looks like it's heading in that direction. So what we're getting is, see, we're getting 1 over x, where x is that value, 1/2, 1/3, so forth like that. You guys see that, at least from what I'm doing with the numbers? Okay, so that's the idea. Now that doesn't prove anything, but at least gives you an understanding of how you could use technology to at least conjecture. And we do that a lot in mathematics. Mathematicians look for patterns. A lot of times you use computers, and then they start getting more into the theory and the proof aspect of it. Okay, so here's basically what we have on the next page. Then we'll start working with some of our derivatives a little bit. So what we have is this thing right here is your derivative rule. The derivative of a natural logarithm is 1 over x, and that's x can only be positive numbers. Okay, you want to understand that if you were working with a logarithm, let me just show you this, and this is important. You can't do a logarithm of a negative number. Okay, it makes absolutely no sense whatsoever. Let me prove that to you. So if you took this, if you tried to do a log base 10 of -1, your thought process would be this. 10 to what power is -1? Is that even possible? No, it's not possible. How about if we did log base 10 of 0? Well, the thought process would be 10 to what power is 0? Is that even possible? No. Logarithms make no sense unless that number is a positive number. Okay, so you're going to find on a logarithm that your graph only is for positive x values like that. Same thing with the derivative. It's only for positive values. So that's how that goes. Okay, then we kind of get into this a little bit. So if you had the absolute value of x, well, then it's 1 over x. But the only thing is on this is x can't be 0. Because if you do an absolute value of x, you get a positive number, right? So you could actually do a logarithm of the absolute value of a number, then it would make sense, wouldn't it? But what if you had the logarithm base 10 of the absolute value of 0? Does that make sense? No. So the idea is when you're doing a derivative of a log of an absolute value, it's still 1 over x, but then you can start working with negative numbers. That's the idea. So the big thing that you want to make sure you have down is this. That's the derivative rule for a logarithm. Okay, so it's 1 over x. Okay, so, and then we have a chain rule that goes like this. Every derivative rule has a chain rule. So the idea with this would be like this. If you're doing a derivative of ln of a function, well, the big rule would be 1 over the function. Just like 1 over x would be 1 over the function, but then you would have to multiply by the derivative of whatever's inside the logarithm, like that. So that's the chain rule for a logarithm, okay? All right, so let's look a little bit at, what I want to kind of finish up with here today is doing a bunch of derivatives, because that's what we're mainly going to get kind of solid with here. So let me look at this one example right here and just show you a couple of things with this then. All right, so if you look at a derivative, what we're going to do is I'm just going to show you what this is. If you looked at a logarithm of absolute value of x. Okay, first of all, one of the things a lot of times students don't get very well is the technical definition of absolute value. Okay, now what I would like you to probably write down is this definition. Please write this down. You've seen this before, but probably you don't remember much about it. We have a definition of an absolute value. It goes like this. If x is positive, or if it's equal to 0, the answer is just whatever's inside the absolute value symbol. You already know that. But if x is negative, the answer is the opposite of whatever's in that symbol. Okay, and you need to understand that definition. I think Calc 2 the other day we were doing some derivative, and I could tell students didn't know this definition, and we had to pull it out to do that derivative. So it's actually very simple. Okay, if this is a positive number, what do? You just take off the absolute value and you get whatever's inside, right? What do you do if it's a negative number? Well, you take off the absolute value, but technically you do the opposite of it. That's what that definition says. It says if that's a negative number, then the answer is the opposite of whatever that number is. Does that make any sense? Okay, you got to think about that and make sense of it. It's not that hard. It's just when you have a negative number there, it changes to positive. How do you do that? You multiply it by negative. That's how you make a negative number into a positive, is you multiply it by a negative, right? So that's what that says. So what I'm doing with this thing is I'm applying that definition. So if you're doing an ln of absolute value of x, if x is positive, then it's just that, right? I mean, if you had the ln of 7, isn't that just the ln of 7? Okay, but if it's negative, well, if it's negative, which is what this is saying, then you would apply that definition. So if you had the ln of the absolute value of negative 7, you would do the ln of negative 7. Okay, because what's the absolute value of negative 7 anyway? It's 7. Okay, so the idea is if this is negative, change the sign. That's all that's saying. Okay, change it to a positive. All right, does that make any sense? Yeah. Okay? The higher you get in math, the more you got to make sense out of these technical definitions. You have to. Okay, so here's what happens then. If you do this derivative right here, if you did the derivative of ln of x, we just get 1 over x. But if you do the derivative of this one, you have to apply the chain rule. So when you do the chain rule, it goes like this. So if you are doing the derivative of ln of negative x, here's how it goes. You go 1 over the function, then you got to do the derivative of that function that's inside. That's applying the chain rule, like that. So what you end up getting then is you have 1 over negative x, the derivative of negative x is negative 1, so you also get 1 over x. Okay, that's what that's showing. Now that's kind of a technical way to show you what the derivative of ln of absolute value of x is. Okay, does that make any sense, or at least some? Okay, I think it's real important that you begin to think through that definition of absolute value and make sense of it, because it shows up from time to time. Like, we haven't done a derivative of an absolute value ever, but if you do, that's the way you have to do it. You have to break it up into 2 pieces like that. Okay, so let's go to the next page and let's go ahead and do the derivatives. That's going to be the number one thing you want to accomplish here, is being able to do these derivatives. Okay, so we do chain rule over and over and over again. So I'm going to do this first one 2 ways, like we've been doing. So when I introduced you to the chain rule, I always said, what is the big function? So what's the big function on here? It's the ln of something, right? So we're going to say ln of u, where u is that thing right there. So u is equal to x to the second minus 3x plus 5, like that. Okay, that's the chain rule. So we've got the big function, then we got the inside part right there. Okay, the chain rule, when we learned it this way, we said dy over dx would go like this. We said dy over dx is equal to dy over du times du over dx. Okay, that's what we learned. So I'm going to do it this way first, then I'm going to show you how to bypass that thought process. Okay, so it's actually very simple. What is the derivative of ln of u? That's what I just taught you. What was that? 1 over u, right? 1 over x, 1 over u. So that part right there is going to be 1 over u. Okay? All right, now what is the derivative of this? 2x minus 3, right? Okay, so the derivative of that is 2x minus 3. Okay? Now, what you got to do on this is, when we did it this way, what did you have to do with the u? You had to plug back in what it was. The u is this part right here. So you want to take this thing, you want to plug it back in, and then we got the answer. So the answer is 2x minus 3, that's in the numerator, and then all over x to the second minus 3x plus 5. So that's how the chain rule goes. If you want to do it that way, that's how it goes. But you're not going to do it that way, trust me. Okay, here's the way you're going to do it. You like doing it this way better, probably. Okay, here's what you do. When you do a derivative of a logarithm, what is it? It's 1 over the function, right? See that? 1 over the function, right? Then you multiply by the derivative of what's inside. The derivative of what's inside is that, isn't it? So you just go 1 over the function times the derivative of what's inside. Learn it in words, that's all you got to do. Does that make sense? 1 over the function times the derivative of the function. Okay, do it that way. I'm not going to do it that first way anymore, but that's how you would go about doing that. Okay, so now this next one, I'm going to do this now with that idea. And if you need to write this down, write it down. 1 over the derivative of the function times the derivative of the function. I'll put a little f function prime. That's how you do a derivative of a natural logarithm, okay? So keeping that in mind, when you do this, what's it going to be? Step 1 is what? 1 over the function, right? It's always going to be the same. Now what do? You multiply by the derivative of that function that's inside, like that, okay? All right, let's see what we know now. Okay, this is going to be 1 over e to the 2t. What's the derivative of e to the 2t? 2e to the 2t. Remember? Itself times derivative of exponent. Okay, you can do a chain rule on that when you do that too. So this derivative is itself, and then the derivative of that exponent is 2. We learned a rule before we even learned the chain rule. So that's it. Now if you put this all together, you're going to have 2e to the 2t all over e to the 2t like that. What's the answer to this problem? Yeah, it's 2. You have some cancellation, don't you? Which you have sometimes when you're working out those problems. So that whole thing cancels, so you're left with 2. That's it. 1 over the function times derivative of a function. Get that in your head, in words, and it'll help you, okay? Okay, so I'm going to let you try the next 2 problems, just the next 2. And then we'll kind of move on and get through some of the ones that have some combined rules with it. See if you can do the next 2 okay. What we got on this first one here to begin with. First of all, what do you do with the 2? You write it down. It's a constant, right? Okay. Now, when you do the derivative of this natural logarithm, there's 2 steps, and you can do it all in your head. It's what? 1 over the function, right? And then what? Derivative of the function, which is what? 2x. That's it. That's an unsimplified derivative right there. Everybody with me on that? Okay. So the answer would be this. You would now just do this all in your head, multiply straight across. You're going to get 4x over x to the second minus 4. So that's your derivative of that function. Okay? That's the rule for a natural logarithm. Okay, the next one goes like this. What you got to see is you have something to the 3rd power. When you do a derivative of something to the 3rd power, what do you do with the 3? Bring it down. You're going to have 3 ln of x to what power? 2nd power. Then what do you got to do? Multiply by the derivative of what's inside. That's the chain rule. Okay, like that. All right, so you have to do that. And you can do this all in your head. You can do this in one step if you want to. Now that's 3 ln of x squared. And then what's the derivative of ln x? 1 over x. That's the new rule you learned. Okay, that's it. That's your derivative right there. Now, you can write it that way, or there's a couple of ways you can write this. You could probably put this in one fraction and write it like that. That's the way I generally write it, like that. Or you can write it this way. You could write it as 3 ln squared of x, like that. That's kind of like how you in trig, how you did sine squared or cosine squared. That's another way to do that like that. Okay, those are very simple, but you got to look at them the right way. Is there any questions about those? Okay, all right, it's all about the chain rule. You got to get that chain rule under control. Okay, let's go to this next one here. What kind of rule do you think would apply to this one? This is a product rule, exactly. Okay, you've got That's your first function. That's your second function. Okay, so we got to do the product rule. So we're going to do f prime of x. So we write down the first. We multiply by the derivative of the second. And we do it backwards. We add to that the second times the derivative of the first. Okay, like that. Okay, and you can bypass it. You can do that. It's all in your head if you want to. So if you do that, what do you have? You have x squared. What's the derivative of the logarithm? 1 over x. Okay. You have ln of x. Derivative of x squared? 2x, right? Okay, that's it. Now we got to simplify it. So one thing you'll notice on this is one of those x's will cross out, right? So that will leave you an x plus, and then I would prefer that you write the 2x in front of the natural logarithm. And that's an okay answer. Is there anything else you could do with that? You could factor an x out, exactly, if you wanted to. You don't have to. But let's go ahead and do that just for the practice. Take the factor of x out. So you'd have 1 plus 2 ln of x. So those would be two different ways to write that derivative is like that then. Okay? Okay, everybody okay with that? Okay. All right. What's that?
ln x times 2x. How come that's not 2 ln x squared?
Okay, because what we did is we did the second. On the product rule, you don't do anything with the second.
No, I know, but then when you go down to the next step, it's
to 2x?
2x.
Okay, that's just, okay, the derivative of x squared is 2x, right? And that ln was never squared. It was never squared. You just brought it down.
ln x times a 2x, wouldn't it be...
Oh, no, I know what you're thinking. I think you're thinking of ln x times 2x, that you multiply those together? Yeah. No, because that thing is married to the logarithm, and it can't be separated from the logarithm. Okay? Can't do anything like that. See, it's no different than having something like this. What if you had the sine of 2 pi times 2x like that? You're not going to say sine of 4 pi x, right? That's outside of that argument. So it's totally separated from that. Does that make sense? That's important too. You want to make sure you have that down. Okay, now let's do this next one here. Let's see what we got going on this one. We have f prime of t. Okay, this is a chain rule. And what you have, what is the big function? It's ln of something, right? So when you do an ln of something, what do? Two things. You do 1 over the function. Now that whole entire function is an ln of the cosine squared of t like that. So it's 1 over the function. That's what the function is. Then the next step is to do the derivative of that function that's inside. Okay, like that. Why did I put an L in there? It's 1 over the function. I don't know why I put an L in there. Okay, so it goes like this. 1 over the function, like that, times the derivative of the function, like that. Okay? And then we can finish this up. So that's 1 over cosine squared t. Now, when we do a derivative of a cosine squared, okay, think of it this way. The way that you probably want to start thinking of this now is write it this way, and then that's going to be a chain rule. Okay? So what do? If you're doing a derivative of a cosine squared, what do? You bring the 2 down to the first power times the derivative of what's inside. That's another chain rule. So you have a chain rule inside a chain rule. So that's 1 over cosine squared t. Bring that down. So that's 2 cosine of t to the first. And then you got to do the derivative of what's inside. You don't have to write all these steps necessarily, but when you're learning, it's probably a pretty good idea. So what's the derivative of the cosine then? Negative sine. Okay, so now what we have is 1 over cosine squared t times 2 cosine t times negative sine of t, like that. And then we need to see if there's some trig stuff that we can apply. That's your derivative. It's not simplified, but that's your derivative. Okay, does that look fairly good?
I can really just do the derivative of cosine squared and make it minus sine squared.
Okay, I'm doing a chain rule on this part right here. Okay, this part right here is what you're asking about. So you're doing something to the second. So what do you do when you do something to the second? You bring the 2 down, leave the inside alone to the first power. That's step 1. Then, by chain rule, you got to multiply by the derivative of what's inside. So when I did the derivative of the cosine, that's what gave me negative sine t. That's what the derivative formula is. So see, if you have anything to the second power, doesn't matter what that is inside the parentheses, the derivative is going to be 2 times that thing to the first times the derivative of that thing. Okay, that's how that goes. That's how the chain rule works out. Okay, let's see if we got any trig stuff going on here. Well, first of all, what happens to one of those cosines?
Cancel.
One of them cancels for sure, right? And then we have times negative sine t like that. So if we multiply that together, we would have negative 2 sine t over cosine t. Any thoughts? Isn't that a tangent? Remember the identity that you learned in trig? You should have learned that tangent theta is sine theta over cosine theta. So I'm going to go ahead and write this as negative 2 tangent of t. Okay, like that. That's the idea. Use trig. Use those identities. You need them. Okay. All right. Any questions? Okay, go for this one here. Go ahead and work that one out. This one is a product rule. And see where you get on this one. This one's not too hard. And then I want to finish up with probably a couple of last things here. We might just barely have time to start logarithmic differentiation too. Now this one you want to apply a product rule on. And there isn't going to be much simplifying I think you'll be able to do on this. So there's your product rule. So once you get that set up in your product rule, I think this one right here is just not going to be hardly anything you can do. You can do that derivative. You can do that derivative. Those are 2 derivative rules you now know. So that's e to the 4x times 1 over x is the derivative of your logarithm. Then you have plus ln of x. Now what's the derivative of the exponential now?
4e.
Right. It's itself, right? Times the derivative of the exponent is 4. That's it. Now, on a problem like this, I would just write this probably as e to the 4x over x plus 4e to the 4x ln x. It doesn't matter what order you put stuff in. The only other thing you could really do on this is you could get a common denominator if you wanted to. I don't think there's any reason to do that. I think that's good enough. Okay, what do you think? That was pretty easy, wasn't it? As long as you know the rules, you'll be okay. All right, so let's go ahead. This next page, I want to do one that's got a lot of stuff on it. Then we'll finish up maybe with one example of logarithmic differentiation. Okay, so what's important about a problem like this is I want you to just think about if you put that in a quotient rule. What does that look like? If you went to a quotient rule, doesn't that look like a big mess? Okay, I have a feeling I may have written something wrong on this thing too when I typed this out, because the purpose of this problem was to show you that you want to be aware of logarithm properties. Okay, so this is typed wrong. Type it, let's redo it this way. It was supposed to say the ln of x, and let's see, that was what, x squared plus 1 to the second all over the cube root of 2x to the third minus 1, like that. That's what I intended to do. Well, the thing is, if you just went to working that thing out, it would be a mess. Let me tell you how you would do this. I'm not going to do it this way, but I'll just talk through how you do this. If you were going to do this derivative, what would you do? You would do 1 over the function, right? Yeah. Then you would do the derivative of the function. When you do the derivative of that function, that would be a quotient rule, right? Bottom derivative of top minus top derivative of bottom over bottom squared. Wouldn't that be a mess? Okay. The thing is, we know logarithm properties. So if you have something like this, you want to see if there's anything you can do first. with logarithm properties. That's the reason I intended to write the problem that way. So let's do log properties. Okay, so this is going to be the same as anytime that you have a log of a quotient, what do? You write it as the log of the top, like that, minus the log of the bottom, okay, like that then. So you want to do that. Okay, now what do you do if you have a log of a product? That's a sum, right?
How come we did ln on the second term?
How come I didn't what?
The ln on the second term?
What do you mean, what second term? I'm sorry.
It's minus ln again. Okay.
Well, what I'm doing is I'm doing the property like if you had ln of a over b, what is that? It's the log of the top minus log of bottom. So that's what I'm doing. I'm just doing the log of the numerator minus the log of the denominator. Okay? Okay, well, how do you do this one? It's product, so what do? Sum, right? Okay, you got the property that says ln of a times b equals ln of a plus ln of b, right? That's why these properties come in handy, okay? So you're going to have ln of x plus ln of x to the second plus 1 to the second minus, and I'm going to go ahead and write that now as 2x to the third minus 1 to the 1/2. Okay, everybody with me on that? You remember doing this in college algebra? Okay, good. That's helpful, okay? Now, let me ask you this. From college algebra, what are you allowed to do with that exponent? Bring it down. Same thing with the 1/2. Bring it down. Okay? So what you'd have is you'd have ln x plus 2 ln of x to the second plus 1. I'm not doing a derivative. Okay? A lot of times students think I'm doing a derivative when I bring that down. No, I'm doing a log property. Then I would have minus 1/2 ln 2x to the third minus 1 like that. So I've done algebra. Okay, that's a typical thing we do in college algebra. And here's one of the why reasons why you do this. In college algebra, you have no clue why you're learning how to do this. Well, it comes in useful, and particularly in calculus when you're doing derivatives. I like doing that derivative. This is an awesome derivative. It's super easy. Okay, all you got to do now is this. What's this derivative? 1 over x. How do you do that derivative? 1 over the function times the derivative of the function. Same thing, see? It's way easier than doing it the first way I had in mind. Logarithms are awesome. They make things easy. Okay, so now let's do the derivative. So dy over dx is going to be this. So this derivative is going to be 1 over x. Okay, go to the next piece. Okay, right here, you have a constant 2. So what we learned is the chain rule. You're going to do 1 over the function times the derivative of the function, which I'm just going to do in my head, which is 2x, right? Then you got the minus 1/2. Same thing, 1 over the function, like that, times the derivative of that inside function is 6x squared. Okay, everybody following what I'm doing there? Now let's just clean it up. I'm not going to do much with this. It looks like I'm going to have 1 over x plus, now when you do this whole piece right here, you can just multiply that straight across, and you're going to get 4x over x to the second plus 1, like that. And then this whole piece right here, well, there is a cancellation you can do on that. So you could do 6 over 2 is 3. So it looks like that's going to be minus 3x to the second over 2x to the third minus 1. And that's your derivative right there. That is the way to do it. That's the moral of that story is do it that way. Don't do it the first way. If you have logarithm properties that you can do before you differentiate, that's the way you want to handle it. Okay? So one of the things we'll do, we'll go ahead and stop there, is next thing we'll do is we'll do the logarithmic differentiation, which takes advantage of the fact that when you have very messy expressions, it's better to use logarithm properties, and then the derivative becomes easier. Does that make any sense? Okay? Yeah, so you want to pay attention to that when you're